the holy grail in a field like string theory or quantum gravity, stated more generally, is for us to somehow go beyond pure mathematics, right? That's what we have been doing for so long. We've been developing mathematical ideas that attempt to combine general relativity and quantum mechanics into some coherent structure that allows us to talk about these two ideas, these two theories at the same time. But we want to go beyond the mathematics to get some kind of contact with observation or experiment, or at least something that stretches outside the abstract symbols that we scribble on chalkboards in physics departments around the world. And recent work by a really insightful group of physicists at least suggests that we just might be on the cusp of achieving that long-sought goal. And amazingly, it's not by virtue of building some space telescope or some incredible collider. Rather, it's by carefully leveraging the power of a quantum computer. And it is an exciting, if highly controversial, prospect that we will be discussing. So it gives me great pleasure to bring in a group of these physicists who happen to also be my friends and colleagues. Joseph Lykken was formerly Fermilab's deputy director and currently leads the lab's quantum division. He's widely regarded for important contributions to particle physics and unification through string theory. Welcome. Thank you.
Good to be here.
Next up is Maria Spiropúlu, a world-renowned experimental particle physicist who is the Shangyi Chen Professor of Physics at the California Institute of Technology. Her work spans the physics of the largest and the smallest length scales, embracing innovation and creativity and seeking new insights to unravel the forces of nature. And finally, we have Daniel Jafferis, who is a professor of physics at Harvard, whose research involves string theory, supersymmetric quantum field theory, quantum gravity. He was awarded the Breakthrough Prize at New Horizons in Physics in 2019 for his transformative ideas on traversable wormholes. Thank you for being here. So just by way of setting context here, I've known these two folks for, I don't know,
Ever?
30 years, 35 years, something like that. We only just recently met, but it turns out that your landlord is somebody that I worked with. Yeah, so I have a connection. I'm keeping eyes on you. Yeah, get the rent checks in on time, please. Yes. No, I'm sure they're always there. So, I want to get into this idea of you guys of potentially using quantum computers to make contact between these ideas that we developed in string theory and quantum gravity and real things that we can kind of simulate and touch, which of course has been something that we've tried to do for so long. And in order to set some context on that, I thought we would begin with these two papers of Einstein back in 1935, which Einstein had no inkling that there was any connection between them, but as we have seen and as you guys have leveraged, we believe that there is a deep connection between them. So sort of jumping right in, imagine it's 1935 when Physical Review gets this paper by Einstein, Podolsky, and Rosen on this idea of quantum entanglement. And again, I think quantum entanglement is a notion that many people have sort of encountered in one form or another, but I just want to sort of take us through it just to sort of set the language, if nothing else. And the rough idea, I mean, we'll get into an example of it, but Joe, when you describe quantum entanglement, how would you just give the basic structure of what it is that they're talking about?
Yeah. The basic idea is sharing. That everything in the universe is quantum, and its structure is made of information. We call that quantum information. And entanglement is when two systems are actually sharing their quantum information. And that's very important because quantum information, it's part of the rules of quantum mechanics that you can't copy it. So you can't copy information that's in a quantum form, but you can share it. And entanglement is when things that may be very far apart, and that was Einstein's problem with it, sharing the same physical information.
Now, in the EPR paper, the example that they focused upon was not the one that we usually use and not the one that's relevant to quantum computers. They used a more pedestrian example that works just as well, of just particles moving through space. But the one that we tend to focus upon, Maria, is spin, particle spin. So just remind us, again, language is difficult to describe these quantum ideas, but as best as you can using ordinary language, what are we talking about when we're talking about the spin of a particle? And I'll throw up some visuals just to sort of give you something to riff off of.
Right. So in these visuals, you have a visualization of the spin as angular momentum. Now, it's a quantum property, so it's not exactly the balls dancing. But if you go one way, the spin is a vector that points one way. If you spin the other way. For those of you who know some particle physics, for example, we have bosons that don't have spin, that have spin 1, integer, and then we have fermions that have spin 1/2, and they have what is shown there. And the spin 1/2 for the fermions, famously, Feynman had a bottle of water and says, this is the spin 1/2. I need to do twice in order to see the world again where it was. And he didn't, so you pick up a phase. It's very interesting. And in the graphic that you have, Brian, there, for the particles that they are entangled, they originally, if you have a spin up and a spin down particle, and they are entangled, and this happens in nature in systems of positronium. For example, an electron and a positive and a positron make a state that is a positronium. If you take them apart, or even at the edges of the universe, and you do a measurement that you measured the one, you don't need to measure the other, you know it.
In fact, we have a visual that I'd love to show to give a feel for that. And just to sort of set that up, Daniel, just for language purposes, if we have a particle spinning one way, the language is we say that it's spinning up. And the alternative, if it's spinning the other way, we have it spinning down. And to really appreciate the weirdness of what Maria was just describing with entanglement, in quantum mechanics, you can have this bizarre state where it's kind of a mixture of spinning up and spinning down at the same time. But then if I go measure that single particle, what will I find? Will I find it in a blend of the two? I mean, in fact, do the measurement with me if you actually. So 3, 2, 1, let's measure it. And when we measure it, we find
a particular direction. That's, in a way, the whole essence of quantum mechanics. I mean, when we measure a property, we always get definite answers. Before we measure it, the answer is uncertain. That's familiar, of course, of just not knowing an answer. But the rules of quantum mechanics somehow treat that situation differently in an unusual way. It's somehow generalization of the rules of probability logic, so that what we could usually do is imagine that before you measured it, it was either up or down, and you just didn't know, but it really knows.
And that's sort of what we're trying to indicate here. It's truly not up or down. It's truly in some kind of undecided, uncertain combination of these two possibilities. And only upon a measurement, which again we can do right here, do we disambiguate and get one particular spin. Now, what Maria was talking about, and Joe, we can just take a look at it, if we are now looking at two of these guys, and these could be, at opposite ends of the universe or something. And now if I go over, and again, if I say measure, I'm going to do the particle on the left. So I'm not going to look at the particle on the right. And according to Maria, if I do that, 3, 2, 1, I only do the measurement on the left. Somehow, what's happened there on the right?
So this is when Einstein called spooky action at a distance, because if you measure one down, the other one will always be up. And if you measure the other one up, the other one will always be down. And that's the entanglement. It's that they're somehow sharing some information about their spins in a way that no matter how far apart they are, once they're entangled, they remember this relationship.
And so if I go back to the unmeasured state, in some sense is the lesson that I can't think of these particles as independent entities?
They are sharing a piece of their physical existence in a way that you can't even imagine classically, but they do it quantum mechanics.
And then, if I go over and I say measure the particle on the right-hand side, then exactly the same kind of thing that we saw a moment ago, the one on the left will now pop out. And so in sharing this information, what can you do with this? And in particular for the work that you're talking about, Dan, I mean, what can you leverage this entanglement to do?
Right. So entanglement itself cannot be used to communicate directly. That's an important point. In that sense, it's similar to correlation, where the two things are the same when you measure them, but whether they were one way or the other way, might have been determined before, right? That's the usual correlation. But with entanglement, one can do a very interesting thing, which is called quantum teleportation, where using an entangled pair, you can transfer a quantum state from, say, the left side to the right side by sending only a classical piece of information. And in many ways, that sounds amazing because, say, in the case of this spin, we can have the superposition of up and down with different amounts. Actually, some of those correspond to the spin being definitely at some angle. And that whole kind of seemingly a lot of information to describe that angle can be sent to the other side just by sending 2 bits, a 1 and a 0, or 2 zeros, or whatever, the result of a measurement.
In fact, so we have a fun little example of that here, if we just to illustrate that. So those transfer of information, it could go, say, from the Empire State Building to the Eiffel Tower. It really doesn't matter how far apart they are. If you have those entangled particles, as you're saying, and you want to teleport that red particle, as you're saying, just bring it into contact with one of the entangled pair, that kind of infects the one in Paris with some of that information, and then get on the phone and make a phone call, send that classical information that allows the person in Paris to pull out the red particle from that process, effectively teleporting it from place to place. Now, Maria, is this just a theoretical idea, or, is this something that people do?
24/7 in the labs. Come watch it. Obviously in 2022, the Nobel Prize was given, and that was 30 years ago when the experiments were done on a table, and the papers were written one-off. Right now in the labs, we have generation of generation and distribution of entanglement, production of entanglement, 24/7, for as long as we can keep the cryostats going. So we have quantum teleportation as a protocol for quantum networks to use a quantum communication language.
So even though we can't do this for a macroscopic scale, on the microscopic scale, this is now a tool. This is not just some novelty.
Yeah, and we have fibers, so things are happening all the time with the Bell state measurement and with Alice and Bob and Charlie that used to be notional exercises. We're doing them in the lab all the time, and we put spool of fiber of 100 kilometers and we do it. It is at the point where the microscopic, the quantum, you use it now as a tool to understand communications and protocols. The traversable wormhole protocol is a protocol of teleportation.
Yeah, as we'll talk about in a moment.
Yes.
It's a good segue because it takes us to our second 1935 paper. So this basically summarizes the Einstein, Podolsky, Rosen paper. A couple months later, there is this other paper, and you can see that there is a similarity in the authorship, except Podolsky's not there. It's just Einstein and Rosen. And Daniel, what was this paper about?
Well, this paper was describing a space-time configuration. Einstein's earlier work in 1916, general relativity, interpreted gravity as curved space-time. And black hole solutions were known theoretically at that time, although they hadn't yet been observed in the 30s. But this was a configuration that looked like a solution of the equations, in other words, that looked like two black holes. If you were on one side or the other, it looks like a black hole, but their interiors are joined. So if you would jump in from one side and I would jump in the other, we would meet behind the horizon in the zone of no escape, but that's what the configuration looked like.
So sort of, vaguely here, some kind of deep indentation in the warpage of space that links up into some kind of bridge, some kind of connection between these two distant regions.
A tunnel in space.
Yeah. And so, as I mentioned before, and just to reiterate, Joe, I mean, these were just two separate ideas. One came from general relativity, the wormhole. The other came from quantum mechanics, entanglement. Any connection at that time that anybody anticipated?
I think Einstein's, if he knew there was a connection, he certainly never expressed it. I think he would be shocked to find out how deeply related they are. And we only started to get the glimmer of that when we started to think about the quantum properties of black holes. And that was a very long road and lots of people to get us to the point where you could even start to make.
So it's not like Einstein missed it or something like that. There was so much architecture that had to be developed. And toward that end, Daniel, one of the key things is, there's two different kinds of wormholes that are really relevant for the conversation we have here. Wormholes that you can get through and wormholes that you can't, right? Traversable versus non-traversable. And just a sort of a fanciful version of a traversable one, just to get us into the mood. If you imagine Manhattan itself as some sort of flexible environment with the Einstein overlord sort of granting us the powers to actually warp Manhattan itself, you could imagine what a wormhole would be. It could be something that takes you from uptown to downtown really quickly. But of course, it would only be useful if when you hopped into a taxi cab or something that you could actually get through that wormhole, because otherwise, what would that bridge itself give to you? So of course, this brings to light the critical question of whether you can actually go through one of these wormholes.
You did, obviously.
Right.
And so this is something that you have spent a lot of time thinking about.
Right. So I think, it was a question for a very long time, really, in a way, since Einstein and Rosen's 1930s paper, whether you could have a wormhole that you could get through. Their solution in the 30s was one you couldn't. You get trapped in it. So it's a connection of space, but you can't make it through. But it wasn't clear whether the equations of gravity allowed a space-time like that, where you could make it through this tunnel. And one of the ingredients that was understood eventually to be important is a certain amount of negative energy. Sounds like an exotic concept, but actually negative energy can appear in relatively ordinary situations because of quantum effects. But in classical world, negative energy sounds like a big problem. And so there doesn't seem to be any ordinary classical solutions that would allow traversable wormholes. I think that put the whole idea of even the non-traversable ones a bit into question of whether it was just a mathematical artifact. I think that's how most people interpreted the Einstein-Rosen wormhole, because you couldn't make it, you couldn't get through it. Maybe it's just an artifact of the equation.
And so you were able to, in a very concrete mathematical calculation, understand what it would take to make one of these wormhole traversable. And it's this sort of negative energy shock wave, if you will, that could momentarily, if not longer than that, open up the wormhole and allow things to get through. And this is going to be vital for the work of yours that we're going to describe in just a moment. But to get there, I now want to talk about the connection. So you've got wormholes, you've got entanglement, and really it's been in the last, decade or so, if I'm being generous with time, that these two ideas were put together. So this is work that we generally credit Juan Maldacena and Lenny Susskind. So can you tell us a little bit about their journey to think about these two things as different facets of the same physics?
Yeah, I think part of the big insight that they made was looking back at this 1935 Einstein-Rosen situation and asking, what exactly is the relation of these two black holes? And they figured out that, well, to really make sense of this, these black holes should be entangled. And I think that was sort of the key insight. Even in the 1935 Einstein-Rosen paper, those two black holes, you should think of them as two entangled objects. And once you do that, you start to think about it in the language of quantum teleportation. And their idea was, well, maybe it's not just kind of like quantum teleportation. Maybe it really is a kind of quantum teleportation.
In fact, they were writing emails to each other. The way Lenny Susskind has explained this to us, because when we wrote the paper, we went to them, both Juan Baldacena and Lenny Susskind. And the way he told us the stories, they were writing emails. They were trying mathematically this equal there. It means equivalent. It's the same. It's an aspect of the same physical reality that seemed so peculiarly far away from being considered. And they were writing emails, and I believe, if I am not mistaken, they published the emails as a paper. It's called R equals CPR. And they published, one with his student also published, because the premise of this also has some other string theoretical, your lane kind of physics. With holography and duality, they published a dummy guide to holography and duality in order to be able to put a sign there. It's highly non-trivial, and there is some conjecture about all of that.
But, everything is clear, 2020 hindsight. But, if you use the following language, a wormhole is a way of connecting, one location to another. And entanglement is a way of connecting one particle across space to another. They kind of feel resonant, but of course only after somebody brilliant makes the connection for you. But in some sense, that's where this ER equals EPR takes us. And what I want to do now, in the remaining time that we have, is now talk about what you guys have done to try to make this concrete, something that we can actually measure. And so toward that end, there is a graphic that I'd like to show. And Joe, do you want to narrate this graphic? And then we're going to break it down step by step by step, because it's going to be too much, to take in one shot. But I kind of want this to be the overture, the preamble, to get the basic idea. So here we go.
So here you see two physical systems that are entangled, and that's what the ghostly line there is. And we want to relate that both to quantum teleportation with entanglement, but also to a wormhole that you can actually move things through. And so that's what the bottom graphic is showing, is something that looks more like a wormhole. And now the idea is that the two pictures that I'm showing you are two different descriptions of the same thing. That I can talk about this in the language of quantum mechanics, and I can talk about it in the language of wormholes, but I'm really describing the same process if you do it right.
So again, just to be clear, you've got particles coming in from the left, that green one, and at the quantum level, you want to teleport it from the left to the right.
Yes.
And at the general relativity level, you want to have it transported from one opening of the wormhole. I make
one of Daniel's traversable wormholes and actually move through it to the other side.
And so your goal is to see this actually happen within a quantum computer, where you'll really be focusing on the upper part of the story. But if the connection is the same, you should be able to use the lower part of the story to gain insight to what's happening, and in that way really link these two together in the most concrete manner. There's also a quick intermediate step that's worth noting. If you were going to try to simulate the upper part of this graphic on a quantum computer, you'd need a lot of qubits, right? I mean, those clouds of entangled particles is beyond the reach of today's quantum computers. So you needed to find a way of simplifying this, and that's a long story that we don't have a lot of time for, but graphically, just so that people know what we are talking about here, you were able to find a small number of these qubits, these entangled particles, small enough that you could actually, in principle, run the upper part of this story on a quantum computer. And that's what made this an actual doable experiment. All right, so that's
maybe
the...
I can say one
please.
quick thing, because you have
Yes,
a lot
definitely.
of AI and ML. So that's for the young people that are doing that every day.
Yeah.
This is gradient descent with level 1 regularization on a neural network. It's simple, but the landscape is huge. And you want to take something from 210 terms of a Hamiltonian to something with a learned program that retains a characteristic of the large one, that Daniel will explain it, but also it can be embedded using 9 qubits.
And you succeeded ultimately in doing that simplification.
And we succeeded to do both the calculation on a relatively large number on the normal computer, on your everyday computer, and also embed the smaller one on the quantum computer and compare simulation. It's like every other experiment. You compare them.
And we'll ultimately see the results. But now, let's just break this down into a small handful of steps. So, what are we seeing here?
Well, this is the two systems that are in an initially entangled state. So, I mean, in some ways, maybe to go back just for a second to something you said before, when you have the Einstein-Rosen bridge wormhole, it took a long time to think of black holes as quantum objects. It's very subtle. And once that realization came, then it was possible to interpret this Einstein-Rosen wormhole as an entangled pair of black holes or two entangled pieces of space. And then going through the wormhole gets interpreted as quantum teleportation using the black holes as your entangled pair. Here we're kind of going the other direction, right? We're starting with the quantum system and hoping that it exhibits features of emergent space-time, so that some of those properties of the wormhole emerge from the dynamics of this
And you can see it in the quantum system. And so, indeed, the idea would be that if these ideas are correct, this simplified entangled quantum system would be associated with some kind of wormhole. And then what you guys did for this next step, what's happening here? So you're bringing in a particle, a qubit.
Right, so the qubit enters the system, and that means that it starts to interact with the degrees of freedom of this system, or in the lower picture, it starts to fall into the wormhole mouth. That's interacting with the degrees of freedom of the black hole, and it begins to spread among those degrees of freedom, and that's something that we see in the top picture. It starts
so that's the green kind of infecting the other
it gets
qubits.
Kind of encoded in the pattern of correlations or entanglement between those green-colored now qubits. And then there's the important step in teleportation where you make some measurement, or you take something from the left and make the phone call to the right. And so that step takes place. The thing we realized is that the actual act of making that phone call, so to speak, and doing the operation on the right, which is critical in teleportation, has the gravitational effect. Information is physical, so especially in the lower picture, if you did that, it will put some fluctuations of quantum fields in from the right, which carry this crucial negative energy. And there's no way to make the negative energy pulse without having gotten information from the left. So it sort of fits together perfectly.
And so that is what would allow the particle to make it through in the wormhole language. And it's the telephone call, like we did from the Empire State Building to the Eiffel Tower, that allowed the quantum entanglement to work. So that's the basic framework. But again, this is an animation on a screen, right? And what you guys wanted to do was to actually take a quantum computer. And so which quantum computer did you pick to work on?
Right. Well, they picked us as much as we picked them. So we used a version of the Sycamore with a few more. So the 2019 version had 53 qubits. It's Google, close to UCSB, close to the Kavli Institute in Goleta. So it Nominally, it had 53 working qubits and 1 not working. We did the experiment in winter of 2020, and we had started this work in 2018, so it took a long time before we arrived to the experiment. Yeah. And the version that we ran it had a few more qubits, so it was 70-something. Some of them were not working. And we used 9 of these, the 9 best in terms of what is called depolarization errors. We used the ones that had 0.3% absolute calibrated qubits. And the way the chips work, which we're seeing there, is you put them in a temperature where the microwaves are manipulating their states and you are entangling them. So entanglement and superposition are happening at the chip level. It's not like the NVIDIA chip, although the way it's going smaller and smaller, it will become also quantum at some point. But this is real, the effects are happening there, and then you can pick the qubits you're working, you can code the gates, you can code the actual phenomenon of what it was in the previous picture. You take a reference qubit, you put it on the left system of the Majorana's, the quantum system. Then you do the entanglement, you do the swapping so that we move from the one to the other side. You put the interaction, you code it, and then you get in a register on the other side, you try to figure out if the teleportation happened. There is a code in there, and there is physics in there. So it's not the same code that we run on the computer farm, on the AI farm at Fermilab or at Caltech. That's not the same codes. The codes are very different. And we see if we were not getting the teleportation, or if the Jafferis protocol was not completed, we would get nothing on the one side. Or if it was, but it was too much errors, we would be swamped in noise. So, at LET and at Tevatron, we did produce a couple of Higgses, but we never saw them because it was swamped with background. So it could have been the case that we saw something completely flat and nothing. It could have been the case that we could see it, or that the errors were at a level that the noise was so tiny that we would see it pop completely. And it would be the case that the errors, even with 1.5 times the errors that we had, we wouldn't be able to say that we saw it. We were barely there. So if you look on the middle plot, you see the actual measurement with the errors we actually had, and you see the case of the wormhole and the case of no interaction. So the no interaction, you can imagine, so is the flat line. If we didn't put the interaction, the teleportation would not happen, and you see it in the flat line in the middle. And if you look at the simulation of that, it looks exactly like the measurement. On the left top, you see if we had tiny noise, 10 times less than what we have, you would see that and that's against the simulation, you would see that the signal would pop very high. And on the bottom, with 10 times more noise, you would see flat line. You wouldn't see anything at all. And on our paper, we put let's say the signal minus background, and both the simulation and the data. And what you see is a smeared out signal. And the flat line on the insert is if you had the 1.5. We wouldn't be able to say anything if we had the 1.5. So we tried in various versions to show that. But the message is that the sycamore was good enough, barely good enough, to be able to do that. And we're trying to figure out other platforms and bigger chips and a little bigger system to learn another system, for example, in order to be able to reproduce this. So what we would like to do is other people to reproduce it, of course, either on such a chip or some other system, a natural system.
So, but Joe, give me the elevator version of
this is really the beginning of something, right? So it's great that, we have quantum computers now where you can actually program quantum physics and say, I'm interested in this quantum physics, and I can actually make it happen on the quantum computer. That's what we're doing here. We're programming a physics experiment. And then as you see here, we're just lucky that the technology of quantum computing has just in the past couple of years gotten barely good enough that we can start to look at this wormhole teleportation. But of course,
I mean, would you consider this having succeeded in doing what you wanted it to do, to show this equivalence?
Yes. So it succeeded in showing it, but it hasn't really taught us anything about quantum gravity.
Yet.
Now, so what we'd like to do is let's repeat this with, say, 50 qubits or 100 qubits with a much better quantum computer. Pretty quickly, as you increase the number of qubits, you will get into a regime where, first of all, I can't predict what's going to happen because on a classical computer, you can't even simulate it anymore.
Yeah.
And secondly, we'll be able to ask some, detailed questions about this correspondence with the wormholes.
I mean, will we, for instance, be able to gain insight as to what happens within a wormhole?
Yes. So for example, it's very similar to what we do in particle physics experiments. Throw things into the wormhole and see what happens by looking at what happens when they come out and what did they interact with? What's inside the wormhole? What are the interactions that are going on inside the wormhole?
I mean, would you summarize this by saying that in some sense you created a wormhole in some poetic or concrete? I mean, this, of course, is where there's been some controversy over how best to describe what it is that you've done. How would you?
Yeah, we didn't drill a hole in the lab.
Right. I mean, I think a good way to answer that question is to start with the following. In some ways, there's a continuum between particles and black holes, right? We can imagine particles like the type produced in colliders, heavier and heavier particles beyond what we've ever seen. But we can imagine that there's a series of ever heavier particles, and eventually we won't be able to distinguish them from a small black hole, a black hole near the Planck mass. But even lighter particles we might think of as highly quantum black holes, even though they're much below the Planck scale, so they're sort of super quantum black holes. And in that sense, you might have interpreted this correspondence between entanglement and the Einstein-Rosen bridge as saying that not only, this is kind of the speculative interpretation of that idea, not only would a large Einstein-Rosen bridge have the interpretation of two entangled black holes, even a small amount of entanglement has an interpretation of some tiny, very quantum filament of space. But that's a bit speculative, of course. What's clearer is that as you start to build quantum systems whose patterns of entanglement and dynamics are of the right type, they have a kind of emergent description, the same way that water waves are an emergent or effective description of the behavior of a pile of water molecules. And they'll have some emergent description that looks better and better described by the equations of gravity. And so this is what we did, I think, is a kind of a first or baby step in that direction. And we think it's the beginning of a period where we'll start to see quantum computers able to produce systems which have more and more of the properties of emergent space-time. And one of the especially interesting things I think about this traversable wormhole situation is we usually thought of the region behind black hole horizons as a kind of inaccessible place, right? They're trapped behind the horizon, so how could we ever really say what happens there? Certainly that's true in astrophysical black holes, but even in our thought experiments, so to speak, of black holes, it doesn't sound very operational, but this shows us that we can sometimes see behind that horizon by making the wormhole traversable. You peek behind what would have been the horizon.
And then you get out.
And so, and then you can get out, exactly.
Yeah.
You can rescue your friend who fell in.
And they can tell you what they saw. So
maybe I can say one more thing, because you asked a very good question, and we have gotten a lot of pushback, and we try to explain that. On the quantum system level, we have completed the teleportation protocol with a system that it is a quantum system, the Sycamore, with 7 qubits on the one side, 7 qubits on the other side, and the reference and teleported. And the signals, the characteristics we saw for the teleportation in the gravitational dual, they could have an interpretation of a gravitational dual system, which we don't know what it is because it's so small. He knows what it is when it is n equals infinity. You mentioned that in your graphic there. So we don't know what the dual gravity is, but the dynamics of it, the observables, the variables, let's say if it was the Higgs, it would be the mass, the momentum, you would have variables that they look that they can have a holographic interpretation in a dual picture. We don't know what the dual system is.
Right.
I think it's fair to
So
say.
Joe, if we can just take us out with one final comment. So, you and I, decades ago, working, on the pure mathematical side of string theory, hoping that the Large Hadron Collider might find superparticles. Unfortunately, you didn't find them for us, but it's not your fault. It's not your fault.
It's a big thing that we didn't find it.
But the
It tells
question
us
is,
something.
do you feel that we may be entering the era that we kind of dreamed of, but in a different way, not through the LHC, but rather being able to probe these strange new realms in this unexpected way using quantum computation?
I mean, it's certainly a different and new way at getting at this problem of quantum gravity, which we know is an incredibly hard problem. So having a really different approach, it's really a very different approach using quantum computers. Maybe it'll lead to some huge breakthroughs, maybe not, I don't know. But having a new tool like that that's really coming out of the blue, I think is very exciting.
And what's your level of excitement about it? I mean, is this something that you like, it's kind of cool? You're like, wow, this is like amazing.
I couldn't be more excited.
But let's say the direct probe is still the collider. You cannot do with a quantum computer what you do with a collider.
Sure.
Yeah.
So let's call them complementary.
Absolutely.
And we're not going to
Different
stop
tools,
colliding.
Different tools, and it's
we're not gonna
exciting to
stop
have
colliding.
any probe that's actually doing real physics and in the same breath talking about quantum mechanics, gravity, string theory, and all the things that are so close to our heart. So thank you all so much for this conversation on this wonderful work.